So, as I mentioned in our video about concepts of motion, in our course we are going to use SI units, meaning the International System of Units. So, distances will be in meters, time will be in seconds, and mass will be in kilograms. So meters we represent as M, seconds S, mass kg, kilograms. There will be times we're given distances in maybe miles or feet or yards. Time could be given in hours or minutes or days. Mass could be grams or milligrams, that sort of thing. So we do need to make sure we're familiar with our prefixes, with our SI units, and able to convert units if necessary. As of now, we are looking at linear motion. So the main quantities we are going to be seeing are position, velocity, and acceleration. The units of these, position we already know is going to be meters. Velocities, distance per time, will be meters per second. Acceleration, being a change in velocity in some amount of time, is meters per second squared. And so we always want to be sure we have SI units as we're running through equations, and want to be able to be sure we are familiar with prefixes as well as our converting. That's what I want. So for example, if we're talking about a velocity, or in this case just speed, how fast something is traveling. So the speed limit on the freeway, for example, is what? 70 miles per hour. And we want to convert that to meters per second in order to use an equation. Now, of course, we can totally Google the conversion and let Google or the internet somewhere take care of it. But we don't get to use the internet when we take the tests. So we need to make sure we know how to convert. I do not expect you to have conversion factors on the top of your head. So we have the test notes. This is my digital copy of the test notes. I am currently on page 2. So the first page, it's not letting me scroll here. So this is the front page of the test notes. There's a whole bunch of constants, which we won't do. Mainly what we'll end up using is gravity. At the bottom of the page, we have the prefixes. So when we say kilograms, for example, kilo, no, I can't write on it. Oh, dang. Kilograms, kilo, the K means kilo when we write kilograms, 10 to the third. So as we are writing out our units, we can write in terms of prefixes, or we can get rid of prefixes, which I'll explain more in just a sec. But in terms of converting units, at the top of page 2, so right here, we have some conversion factors. They're separated out based on the conversion. There's conversions for length, so the inches to centimeters, or inches to meters, or miles to kilometers. Volume, velocity, this is the one we want. Now we have two different written out. 1 mile per hour, I'll go ahead and write that one over on our second screen. 1 mile per hour is equal to 0.447 meters per second. So saying 1 mile per hour is the same as saying 0.447 meters per second. Whenever we want to convert units, we want to take this conversion factor and write it either as 1 mile per hour divided by 0.447, because that equals 1. If they are equal to each other, if I just divide the 0.447 to the other side, that leaves me with 1. So I can write it that way, or I can write it as 0.447 meters per second, divide the 1 mile per hour over, and that still equals 1. Which one I want depends upon what units I'm trying to get rid of. So in the case of this speed limit, and wanting to convert from miles per hour to meters per second, I want to choose the ratio that has the miles per hour in the denominator, because I can cancel out the miles per hour in my original number with the miles per hour in the denominator. And so I end up multiplying the 70 by the 0.447, and now we have units of these meters per second. 70 times 0.447 is 31.29 according to my calculator. Now this brings up another important concept. Significant figures. Now, don't let that incite fear in you. You might have had classes where they're very particular about your significant figures. I do want you to pay attention to significant figures, but when it comes to a test, if you're off by 1, maybe 2, I'll still give you credit, and full credit if your answer is correct. If our starting number, as in this example, is 70, and you try to give me 31.29, I might be not so lenient, though I guess that's off by 2. Significant figures, we're going to base our answer that we give off of the numbers given in the problem. So 70, I just brought up the number 70 miles per hour because that is the speed limit on the freeway. Now, typically the trailing zeros are not significant. We're going to go ahead and just assume this to be 2 sig figs. That we know, well, we know the speed limit is exactly 70. So that means we know the speed limit to 2 significant places. We don't say that the speed limit is 70.3. We don't say it's 69.7. It is 70. And so we have 2 sig figs here. We always base the significant figures in our answer off of the numbers in the problem, and always based off of the number that has the least significant figures. Of course, in this particular example, we're only converting the 70, so our answer needs to have 2 sig figs as well. So we would say that 70 miles per hour is 31 meters per second. We cannot know that any more accurately, even though the conversion factor is more accurate. Now, I remember as a student always wondering how to tell if the zeros were significant or not. And I finally discovered that if I wrote my answers in scientific notation, I could better determine if my zeros were significant or not. For example, let's say I have a number, 7450. I don't really care what the units are at the moment. But let's say in our problem, we need 2 sig figs in our answer. I would often write this in scientific notation, but now I know I just need 2 sig figs, so I would round that. Since the trailing is a 5, that 4 rounds up to 5. And that is my answer in 2 sig figs. If I have a number, say I was given a number, let's not do that one. And I was asked how many significant figures are there. Again, I would write this in scientific notation. Let's see, 1, 2, 3, 4. Count my decimal place over. And then I could see that there were 3 sig figs. When it comes to solving problems throughout the semester, wait until the end of a problem to round your numbers to the appropriate significant figures. And again, as long as you're within 1 sig fig of what it should be, that's fine. I'm not going to harp on scientific notation too much. But I do want to see that you're paying attention and that you do realize that just because your calculator screen is full of numbers doesn't mean you actually know those numbers that accurately. Okay. One other thing to keep in mind is intermediate steps. Meaning if you had to solve for time and then you had to use time to find a distance, the numbers must have more sig figs than the answer. You can never be more accurate than your whatever number is rounded the most. Now, I do now and again get questions about why sig figs. And that's a perfectly legitimate question. So let's say I had a piece of hair that I've laid down on the table. And I ask all of you to pull out a strand of hair and grab a ruler and measure how long that strand of hair is. So you take your nice little ruler out, you line it up. So let's see. These are, I assume, inches. So 1, 2, 3, 4. I'm not lined up very well. Let's try that to get a little better. No, it doesn't like. Okay. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.2 is what it looks like. inches. Now I can't say 12.22 because I can't read this ruler more accurately than the millimeter. I mean, I might be able, here it looks like it doesn't even go quite halfway between the millimeter marks. And so that's why I'm going to stay at 12.22. You can sometimes guesstimate maybe half-ish of a millimeter, but it would not be actually purely accurate because I can't really eyeball that super well. So I would say this number is significant to 3 sig figs. I can measure this line, which is representing a piece of hair, for example. I could measure this line accurately to 3 sig figs. This is the whole point behind significant figures, is how accurately can I measure things? And that completely depends upon your measurement tools. For example, what if I asked you to measure the thickness of that piece of hair or this line? Well, I can certainly rotate the ruler and line it up, but it looks to be just barely bigger than the line on the ruler, which I don't know how big the line itself is. It's certainly a lot smaller than a millimeter, but my ruler is not able to measure this. I would need some sort of different tool that was able to measure much smaller thicknesses, much smaller distances. And so I can't claim that this line has a thickness of 0.22 millimeters because I can't see that gradient on the ruler. Significant figures all boil down and come from this idea, and not the idea, but the measurement tools that we use. We can only be as accurate as the tools themselves, and so we cannot claim more accuracy in a final number. So we just have to keep that in mind as we go along. Now I'd like to do one more unit conversion for you, because something that it can be a little more complicated when we get to, say, like density. The density of ice is approximately 900 grams per, kilograms per meter cubed. So that's already in SI units, because we have a mass, the kilograms, that's a totally SI unit. Meter, even though it's cubed, meters are SI units. So this would be the SI units of density. But let's say we have some wood, and the density of this wood is 0.76 grams per cubic centimeter. We don't have SI units here because mass grams, that's not SI units. We can certainly get to kilograms, of course. And then centimeters is not SI unit. We need meters to be our SI units. And so we need to convert these. Now, in terms of converting and dealing with prefixes, going back to the test notes, this bottom table on the front page is all these unit prefixes that we can see. So again, kilo, 10 to the third, means kilograms is 10 to the third, or 1,000 times bigger than grams. We can use that information as a conversion. So if kilo is 10 to the third, that means a kilogram is 1,000 times bigger than a gram. Or we can say that it takes 1,000 grams to make up 1 kilogram. And that will allow us to cancel out the grams. So we have kilograms in the numerator now, but we need to get rid of the centimeters and convert it to meters. We could look on the table, centimeters right above kilometers, kilo, the C, 10 to the negative 2. That means there's 100 centimeters in 1 meter. What that does not mean, there's most certainly not 100 cubic centimeters in a cubic meter. If we want to go from centimeters to centimeters cubed, we have to cube the whole thing. So 100 cubic centimeters, 1 meter cubed, or just write the conversion as 100 over 1 and then cube the whole conversion. So our answer, the centimeters cubed will cancel out. We'll have the 0.76 times 100 cubed over 1,000. And then the units will be kilograms per meter cubed. So we would end up with 0.76 times 100 over 1,000, which you can totally, of course, use a calculator to solve. We would get 760 kilograms per meter cubed. Okay. So conversion factors using and converting will come in handy throughout the course of this semester. And again, I just want you to be aware that those conversion factors are in the test notes, the ones that you may need. So when it does come to a test day, that you can find them here and convert. Some of these you won't need. We're not going to be talking about mass and energy. We talk about that more in physics too. So that will come in handy then, perhaps. All right, you should be able to solve problems in this first chapter. Make sure you're thinking both conceptually and in terms of solving the equations and approaching problems in general. And as always, please know you can reach out to ask questions.